Hello everyone, I'm Monica Chiosa, and together with Fabio Maschi, we are going to present you our work on hardware acceleration of compression and encryption in SAP HANA. This is a joint collaboration between Systems Group at ETH Zurich and SAP. Cloud computing is here to stay. Its flexibility in both deployment and scalability has made businesses to adopt it in their customer solutions. Besides flexibility, the cloud is able to offer access to a large selection of hardware infrastructures, being them CPUs, GPUs, SmartNICs, or FPGAs, and making possible and simpler the optimization and customization of offered solutions. One such example is Project Corsica, an ASIC-oriented streamlined compression and encryption pipeline that has been designed to address the storage needs and service quality guaranteed by Azure's data storage. In our work, we focus on the analysis of enhancing SAP HANA, SAP's software as a service in-memory database with FPGAs. More specifically, we look on how I/O path operations, such as compression and encryption, can be offloaded to the accelerator. In databases, we differentiate between three states of the data. At rest, when it is not used and it is stored on physical or logical devices, in transit, and finally, data can be in use when it is employed by the user. For services offered in the cloud, where hardware resources can be shared among multiple users, data must be encrypted when it is at rest and when it is in transit. This is also an SAP corporate security requirement. There are also constant efforts towards securing the data when it is in use, one such example being total memory encryption from Intel. More than securing the data, storage and communication bandwidth must be minimized. For this, databases use both light and heavyweight compression algorithms. Currently, just like many databases, SAP HANA uses deflate compression and AES encryption algorithms. The deflate algorithm consists of complementary steps. On one hand, LZ77 compression reduces the payload by removing data duplication using search window and pointers. On the other hand, Huffman encoding encodes the data coming from LZ77 compression using the minimum amount of bits for very frequent symbols. For encryption, SAP HANA uses AES, asymmetric key encryption with efficient software and hardware implementations due to its architecture based on permutations and substitutions. AES operates on 128-bit words and employs different key sizes. Out of the multiple block cipher modes, we are interested into ECB, counter, and CBC modes and analyze them from the 256-bit key size perspective. ECB is the simplest of the modes by having only the transformation rounds on the data path. It is parallelizable for both encryption and decryption, but has the limitation of being the least secure of the three modes. CBC is the most secure of three, but its advantage comes at the cost of having a data path dependency while encrypting. This data path dependency between the plain words of a data block causes the mode to be less parallelizable. Counter mode represents the sweet spot between security and parallelization for both encryption and decryption. We combine both standalone designs for compression and decryption into a single streaming pipeline that keeps track of the ending of one data block and the beginning of a new one by enhancing the data path with a control signal. In color, you can notice all the streamlined OpenCL kernels that are running independently of the host program. When utilizing encryption in CBC mode, we add 4 AES encryption modules such that we could match the compression throughput performance. We implement both operators separately and working together on the FPGA. The FPGA resources are divided into areas: a static area named port support package, which takes care of the communication between the FPGA and the external devices, such as DDR memories or the host processor, and the dynamic area that comprises of the logic allocated for the compute kernels. For our experiments, we mimic SAP HANA I/O traffic pattern from the host processor. Keep in mind that in a production deployment, the database would run on the host processor. The application uses OpenCL for FPGA framework to send data directly to the memory of the device. After the data has been sent, the compute kernels can start processing it, synchronizing with the host as soon as the compute operation has finished.
To evaluate our design, we need to characterize the pattern of I/O traffic traces produced by SAP HANA. For that, we used TCP/H benchmark data to feed the database and collect the traces generated to systems call. This is a representative workload that mimic common operations of SAP HANA, such as data loading, replication tasks. Based on the TCP/H data loading and unloading, SAP HANA produces the following I/O traffic. 90% of the data read is done in blocks equal or larger than 64 kilobytes. For data write operations, about 50% of the blocks are equal or larger than 64 kilobytes. All log reads are 64 megabytes, while writes have a heterogeneous size, but 64 of them are exactly 116 kilobytes. We compare optimized implementations of compression alone on the CPU versus on the FPGA. For the baselines, we used up to 2 CPU threads, since this is the maximum number of threads allocated to such operations in the current deployment. The FPGA has a clear advantage over the CPU, and the speedup is better for bigger block size. Here, we see that the maximum throughput for compression is 4 gigabytes per second, about an order of magnitude higher than on the CPU. The I/O traffic traces we collected show that more than half of the data write operations have a payload of 64 kilobytes or bigger, so would highly benefit from an acceleration by the FPGA. The compression is a very expensive operation. Several attempts to move it to hardware did not show promising results. In our scenario, we integrated the compression of I/O requests on the CPU, so data transfer remains compact. Now we proceed to the evaluation of AES encryption alone. Note that B and C graphs are on logarithmic scale. The first mode, CBC, has a lower throughput because of the data dependency in the algorithm, which grants it a higher level of encryption compared to the other at the cost of a lower computation. The key point here is that encryption reads up to 15 gigabytes per second on the FPGA, and the I/O traffic traces we collected for write operations have a payload in the range where the FPGA is similar or better than the CPU for the counter and ECB modes. Offloading decryption to the FPGA has a consistent higher performance across the different modes. The range of data size generated by SAP HANA also lies in favorable range for an acceleration on the FPGA. Now we proceed to the full FPGA pipeline of compression followed by encryption. With the exception of blocks smaller than 8 kilobytes, offloading both operations to the FPGA has similar or better performance compared to the CPU. The range of block size where the acceleration is not favorable represents about only 5% of all write operations combined. As we saw in the standalone evaluation, compression has a maximum throughput of 4 gigabytes per second, therefore being the bottleneck of the design. This gives an interesting point. As long as the compression algorithm remains the bottleneck, the cost of using CBC, the more secure encryption mode, is not that high, making it a suitable choice for important use cases. We also performed evaluation of batch processing requests, so combining small blocks together into a single FPGA invocation. And we report results and discussion in the paper. To conclude, databases can profit from offloading computing-intensive tasks to accelerators, and the cloud makes it affordable. For compression and encryption, placed on the I/O path, we have over 1 order of magnitude gain on throughput. Nonetheless, compression is the bottleneck, so more optimization is required into this direction, or different algorithms need to be considered. Thank you.